Okay, let's go ahead and review the Lewis structure homework you had for from Monday. All right, so let's follow the rules that we know, which is number one, you count up the Lewis, the valence electrons, and then you have your central atom, and then you decide whether you should do single bonds, double, triple, and then you count up whatever's left over and put your lone pair. So let's start with Pi3. So Pi3, your phosphorus has 5, iodine has 7. 7 times 3, you have 21. So plus the 5, we have 26 electrons that we need to account for. So we're going to put phosphorus in the middle, 3 bonds because we have 3 iodine. And phosphorus is a group 15 element, so it wants the 3. So now I have 6 that I've used up, and I need to account for 20. I know that phosphorus has 5, it used up 3, so with each bond it uses up 1, so there's 2 left over, that's my lone pair. Each iodine has 6 left over since it used, I don't know why I did that. Since it used up 1, there's 6 lone pairs that we need to account for. Okay, OneNote is not cooperating with me right now. Here we go. All right, so that's what Pi3 looks like. Nitrogen. Nitrogen has 5 valence electrons and there are 2, so there's only 10. And since there are 2 elements here, and they're the same element, so obviously there's, let's say we make 1 bond. Well, that's not really gonna work. Why isn't it going to work? Because nitrogen doesn't satisfy the octet. That way, if there's 1, there's 3 left over, right? And 4 left over here, so it's going to use up 1. There's 5 of them total, 4 of them, and then that wouldn't be enough for this nitrogen. But if we use 3 electrons and triple bond the nitrogen, then each of the nitrogens gets its valence electrons filled because it has 5. It shares 3 more with the neighboring nitrogen, so now it's all satisfied with the octet. All right. Next one is water molecule. So water has 2 hydrogens and an oxygen. Here's the thing about hydrogen. Hydrogen is an exception to the octet rule. Hydrogen only has 1 electron, so it wants 1, so it's happy with just 2. Having said that, you've already seen water molecule probably look like this many times. So you can draw it this way, or you can, of course, draw it regular way. And then you can put the lone pairs like that. But hydrogen only has 1. It shares 1. Oxygen has 6. So it makes 2 bonds, and they're all satisfied with the octet. Now, arsenic requires 3 bonds, right? Because it has 5. And so bromine has 7. So we're looking at something similar to the Pi3. The Pi3, because arsenic also has 5, so it's going to look like this. Okay, and then you put all the lone pairs. Okay. All right. Now, silicon tetrachloride. Silicon is a group 14 element, so silicon has 4 valence. Chlorine, has 7. 7 times 4, you have 28 plus the 4, so 32 valence electrons that you need to work with. You put silicon in the middle. Since there are 4 chlorines, and remember silicon is a group 14 element, and they really like to share, right? And they like to make these single bonds for the most part. And then you have all the lone pairs. Oh my God. All the lone pairs, which my OneNote just kicked me out. Give me 1 second. All right, back to silicon. All right, so silicon has 4 valence, chlorine has 7. Then we're going to put silicon in the middle, chlorine surrounding it. And then we'll go ahead and put all the lone pairs. I don't know why OneNote is not working with me today. Okay. And oh my God. So that's what that looks like. HCl, you know, hydrogen is an exception to the octet rule. So it's just going to make one bond with chlorine, and chlorine is happy with its one bond because it has 7 valence. FCN is fluorine, carbon, and nitrogen. So now let's look at this one. Fluorine, you know, is going to always make a single bond. It has 7 valence. Carbon has 4 valence, and carbon and nitrogen like to multiple bonds. So think of that when you're forming this compound. So fluorine is going to make its one bond to carbon, right? And then that's really done, but you still have nitrogen and you still have carbon to worry about, because after all, carbon here is not satisfied with its octet at all. So if we can multiple bond it to nitrogen, now what is this multiple bond going to look like? All right, sorry, for some reason OneNote keeps on kicking me out. So carbon and nitrogen, if they triple bond together, then that satisfies carbon's 4 bond need, nitrogen's 3 bond need. Nitrogen will still have a lone pair, but this is the only way to satisfy that octet. All right. And then we have HNO. Again, whenever you see nitrogen, carbon, oxygen, multiple bonding is always a possibility, especially when you don't have enough elements. And in this case, if hydrogen makes its one bond to nitrogen, now nitrogen requires its multiple bonding because there's no other way for these elements to satisfy their octet. So that's what that's going to look like. And then the last one, you have nitrogen that wants 3 bonds, each hydrogen wants 1, and then there's a lone pair on the nitrogen. So that's what that looks like. All right, so that's it for the Lewis structures. It's very important to just do some practice ones, and I will post more when I get back. I'll go ahead and post more, and we can meet during bonus before your quiz on this bonding in order to review a little bit more. Okay, the next thing we have, and the last thing before that you need to know for the quiz that's going to be the day before Thanksgiving is naming. And so we're going to start with ionic compounds, and then we'll move on to covalent. Okay, so let's talk about how we name ionic compounds. There are 2 kinds of ionic compounds we're going to talk about. This is type 1. It's just binary. So you have 2 ions. One is a metal, one is a non-metal. The cation, that's your positive ion, is always written first and named first, and it doesn't change its name at all. The anion, that's the negative ion, and it's going to change the ending to IDE. So chlorine is going to become chloride, iodine is going to become iodide, and so on. So let's look at these. You have sodium, right? And you have chloride. So you're going to be given the charges and the elements. How do you put them together? So first, how do we put them together? It's whatever the positive and the negative are, they have to add up to 0, right? So in the case of sodium chloride, it's a 1-to-1 ratio. So you have 1 sodium to 1 chloride. You put them together and you don't need any multiple ions, right? So 1 sodium and 1 chlorine, you don't ever write the ones, but that also indicates just writing it out this way indicates that there are ones here. We just never write them. So how are we naming them? We're always starting with the positive. That's always getting its regular name. And then chlorine, which is your second one, is going to change this ending and it's going to become chloride. Same thing with all the other ones. So if it was iodine, it becomes iodide. Sulfur, as you can see here, becomes sulfide, bromide, oxide, nitride, right? So they all are going to drop the ending and form IDE. Now, let's look at ones that don't have just a 1-to-1 ratio. What if we have calcium? We know calcium is 2+ because it's a group 2 metal. And what if we have calcium and calcium wants to bond with fluorine? And fluorine is -1. So how would we put these together? Well, if calcium is +2, that means we need 2 fluorines per calcium atom in order to make it a neutral compound. So it's going to be CaF with a subscript 2. So think about having these kind of crisscross, right? Like if you were doing a common denominator, right? You would want to make sure that both of them have the same. So by having 2 next to the fluoride, that indicates that you have 2 fluoride ions. And that means that 2 negative cancels out the +2. And we name this calcium fluoride. So the fluorine becomes fluoride. And then you can see the same thing with aluminum oxide, right? Oxygen becomes oxide. Aluminum, you can see here is +3. Oxygen is -2. And you're crisscrossing. You're really finding a common denominator. So if you have 3 oxygens, right here, that's -6. 2 aluminums, that's +6. +6 -6. Your compound is neutral. So that's one group of ionic compounds. The other group of ionic compounds are type 2 compounds, where it's the same concept except that now we have Roman numerals involved. And this is because remember how we said transition metals don't really have an exact charge. Like I can't say if it's in group so-and-so transition metal has this charge. We can't say that because of those D block elements, right? So because they have partially filled D blocks, and sometimes they can lose 2 electrons, sometimes they can lose 3. So we indicate the charge with Roman numerals. And so here's what that looks like. You'll be given the table. So Fe can be 3+ or 2+. So when it's 3+, we call it iron 3 with Roman numerals. Back in the days, that used to be called ferric, and that's where Fe comes from, by the way, ferric, that's the Latin word. But this older name part, you don't need to know. That's just FYI. So copper, if it's copper 2, then it's Roman numeral 2, copper 1. So all of the transition elements come with Roman numerals. So when we're naming them, we add the Roman numeral on there. So FeCl3 is iron 3 chloride. Where does that 3 come from? Well, you know that chloride is -1 and we put 3 of them there. So which means iron must have been +3 here in order to, again, make a neutral compound. If we have FeS, for example, here, that's iron 2 sulfide. And again, the naming is the same. The negative ion, the anion, still gets the ID ending. Sulfur becomes sulfide, nitrogen becomes nitride, oxygen is oxide, phosphorus, this should say phosphide. But now you also are adding a Roman numeral, okay? And the Roman numeral has to do with the charge of the metal ion. Okay, now let's do some examples of how we go about naming them and writing the formula. So we're going to just start with this 5, and this is all we're going to do right now together. This 5 here, and then this 5 there. So let's start with the naming part. KCl. So you look at the periodic table, you know K is potassium. And then you know that chlorine is going to become chloride. So that's just potassium chloride. Li2O, it doesn't matter for our purposes right now for naming part that it's a 2 there. It's still lithium. And then oxygen becomes oxide. Number 3, CaBr2, it's going to be calcium bromide. Then you have LiH, so the first metal, lithium, and then hydrogen becomes hydride. And then MgBr2, magnesium bromide. Ooh, bromide. Now, to write the formula, you need your sheet of all the ions, which I will post on my JAG, which will be there under topics, where it says ionic and covalent compound naming. So sodium bromide. So you look at the chart, you're going to see sodium is +1, bromide is -1. When it comes together, it looks like this. Calcium oxide. Again, you go to the chart, you find calcium, you find oxygen, and you can also find it just from the periodic table, right? And it's going to be CaO, not Ca2O2, because it's a 1-to-1 ratio. 3 is silver chloride. Silver is one of those that is always +1. It's the only transition metal that doesn't have a bunch of different charges. And chloride we already know, so it's going to become AgCl. Silver oxide, again, Ag is +1, oxygen is -2. Now, in this case, we need 2 silvers, right? So we put a subscript for each oxygen. Aluminum nitride, so we find aluminum from also group 13 or from that sheet of ions, and you're going to have nitrogen. And since it's a 1-to-1 ratio, it's just going to be AlN. Okay, so classwork/homework is going to be the rest of this worksheet. So you're going to name those, and you're going to write the formulas for those using your sheet of all the ion charges when you're writing the formulas. Naming part, you really just look at the periodic table and then change the name of the second one, which is the negative. So oxygen is oxide, sulfur is sulfide, nitrogen is nitride, and so on. So you do that now in class. What you don't finish in class becomes homework, which will be due next period, and I will go over it before we talk about how to name covalent compounds. All right, have a wonderful day.